Welcome back, guys. If you remember last time, we built a graph that works out gradients, but we only tested it with addition. And with addition, if you remember, it just passes the gradient straight through. So today we're going to look at three things. We're going to look at multiplication, which actually depends on the inputs. And then when I was writing this, I discovered a sneaky little bug that we'll take a look at. And then we'll actually look at the proper way to prove that this is working and look at our first neuron. So first thing, let's go ahead and build out our multiplication rule. Structurally, it's the same as addition. You borrow inputs, make an output node, then store a backward function. The only thing that really changes is what the function does. Example is for a times b, the derivative with respect to a is b, and with respect to b is a. So each input's gradient gets scaled by the other input's value. That's the cross, and it's the first time the gradient actually depends on the numbers going through. Addition passed it through untouched. Multiplication actually scales it. Right away with this, as I was writing it out and testing, I found another interesting thing that Rust does. So my multiply function needs to read one's input value while it's writing to its gradient. And if those overlap, or if it's the same node, refcell actually panics or errors out on this. It gives us the already borrowed error. So we remember refcell checks the rules at runtime. So instead of not compiling, it just crashes while it's running. The fix is easy once you actually see what's going on. You just have to read all the values and put them into plain local values first, which that lets go of the borrow, and then you do the writing. That's the trade with refcell as far as I can tell. You get the power to change a shared node, but the safety net moved to runtime, so it's not exactly a mess up. And as you can see at the end of the clip there, the test is now passing, so it's giving us the correct uh, A is 2, B is 3, then you run it as A's gradient is 3, that's B, B's gradient is 2, and that's A. The cross derivatives are right, so multiplication is technically working right currently. So the real test that actually matters in this situation is what happens when a value gets used more than once. The simplest use case for it is a times a. In calculus, it says the derivative of a squared is 2a. So say a equals 3, the result should be 6. So let's see if the engine agrees, but we find a nice little bug when this happens. All right, so here's the thing. When a value feeds into more than one spot, its gradient comes back from more than one path. And those have to add up. And that's the chain rule again, if you remember from our episode 1 explanation of it. Now, watch what happens if we change these equal signs to plus equals in that backwards function for a times a. The function pushes a gradient into a twice, as both slots are the same node. Each push is 1 times 3, which is 3. With plus equals, 3 plus 3, that's 6. Correct. With just equal, the second push overwrites the first, so you just get the 3. And this is the part that I wasn't prepared for, and what makes this actually nasty. It's exactly half, so it comes out as totally silent, and it gets worse. So my earlier test, the A and B, one uses different inputs, so each one only gets one gradient. It passes even with this bug in there. The bug's completely invisible unless a value gets reused, which is the lesson here. A whole class of bugs only shows up when you reuse a value, so you've got to write that test on purpose. Passing the easy cases doesn't always mean that your code's correct. So if we change this back to plus equals, and we use this reuse test, a times a is 3, gradient of 6, the plus equal is right. But passing like a select few tests that I'm handpicking, that's still not really proof. I need to check the whole thing against something that's independent. And this is generally called a gradient check. And it's honestly super simple. Remember, a derivative's just a slope, how the output moves when you nudge the input. So I'm literally just going to do that. Nudge each input by a tiny amount up and down. Recompute the output with plain arithmetic, no graph, nothing. Just measure the slope. And I'll put the formula on screen here. We'll do this, and if that number worked out with zero autodiff machinery matches what the engine came up with, uh, using all the graph enclosures, then the engine's correct, not just on the cases I've thought of, the whole thing itself. So let's run it on an expression that mixes multiplication and addition. They match better than 1 part in a million. And that's it. That's not a situation of it seems to work, that's proof. And everything I build from here is going to be standing on an engine that we know is right. So I think now it's time to make this thing real. Let's build one actual neuron. So the example of our neuron will be W times X plus B. That's a weight, an input, and a bias. It's the smallest piece of a neural network that there is. So we'll look at the gradient of W is X, the gradients of X is W, the gradient of B is 1. And that's exactly what calculus says that it should be. Worked out by the engine, you get the same. So this tiny thing is called a seed. A network's just thousands of these stacked up and trained with exactly these gradients. So next time what we'll do is we'll turn these single numbers into tensors, whole arrays at once, and start building, real numbers and real layers. Then we'll use the same engine underneath. The numbers just get bigger, really, and you know that's what leads into the question of this entire series. We're gonna make the AI play games. The question is, will the memory assisted in transferring learning between games? So we'll see what happens. Then I can't wait to watch this blow up on camera. You know what? I'll see you guys next time when we build the tensors.